Okay, let's dive right into this explainer and explore the totally fascinating question of what the world around us is actually made of. Have you ever just stopped for a second, looked around, and wondered what fundamentally connects the water in your glass, the air you're breathing, and the screen you're looking at right now? Well, today we are taking a journey from the visible, everyday items we interact with all the way down to the invisible chemical building blocks that make up our entire reality. We are going to give you a total, detailed explanation and unpack the complete nature of matter.
To make sure we cover absolutely everything, we're going to build a mental map together by stepping through this agenda. 1. What is matter? 2. Exploring everyday mixtures. 3. Is air a mixture? 4. Understanding pure substances. 5. Elements versus compounds. And finally, 6. The building blocks.
Let's kick things off with section 1. What is matter? Seriously, take a second and just look around you. The clothes you're wearing, the water you drink, the food in your lunchbox, the trees outside, or even the staircase you climb every day. All of these consist of matter. And as we know, matter is made up of incredibly tiny particles. But here's the thing, most things aren't just made of one single type of particle. They're complex combinations. Our goal today is to understand exactly how these different substances come together, how they interact, and how we categorize the whole shebang in science. Moving right along to section 2, exploring everyday mixtures. Think of science kind of like cooking. You really don't need a lab coat to observe complex chemistry. Dishes like a delicious plate of poha or a fresh sprout salad are perfect everyday examples of mixing several ingredients together. In these examples, it's like a giant puzzle where you can actually still see the individual pieces. The chickpeas, the onions, the tomatoes. They're all mixed together in the bowl, sure, but they haven't fundamentally changed what they are. And that brings us to a really critical scientific definition. A mixture happens when two or more substances are combined, but, and this is the absolute key detail here, each substance retains its own individual properties. The components do not react chemically with each other. This means the green gram in your sprout salad is still just green gram. It hasn't magically transformed into a brand new chemical entity. So, the crucial point here is categorizing these mixtures into two specific types based on how they actually look. On one hand, we have non-uniform mixtures, like our salad or sand mixed with water, where the different components are completely visible to the naked eye, or maybe with a magnifying glass. But on the flip side, we have uniform mixtures. Think of sugar entirely dissolved in a glass of water. The sugar particles are evenly distributed and completely hidden from view, literally invisible even if you look under a microscope. The entire mixture appears the exact same throughout. Now that invisible, uniform mixture of sugar water leads us perfectly to our next question. Which brings us to section 3. Is air a mixture? This brilliantly illustrates that mixtures aren't just liquids or solids. They exist across all physical states. Air, for instance, is actually a uniform mixture of gases. It's composed of about 78% nitrogen, which, fun fact, doesn't actually help with combustion, along with the oxygen that keeps us alive, plus argon, carbon dioxide, and water vapor. We also see other fascinating combinations out there, like mixing a liquid and a liquid to make vinegar, or a gas and a liquid to make aerated soda water. But let's look a little closer, because air isn't purely gas. If you try this at home, just taking a clean black piece of paper and leaving it near an open window for a few hours, you'll discover something else entirely. When you check it later with a magnifying glass, you'll see tiny solid dust particles settled all over the surface. These particles are basically suspended in the air. They aren't an integral part of the air itself, but are considered pollutants. And their presence actually makes the air, in certain times and places, a non-uniform mixture of solids and gases. Before we leave the topic of mixtures, here's a really fascinating piece of scientific history. Did you know that solid and solid mixtures can be uniform too? We call these alloys. Ancient Indian texts, like the Charka Samhita, refer to these as Mishra-loha. For example, bronze, also known as kamsya, is an alloy made of 4 parts copper and 1 part tin. Amazingly, it was historically used in medicine to improve digestion and boost immunity. Today, we use alloys literally everywhere. I mean, think of stainless steel. That's just a uniform mixture of iron, nickel, chromium, and carbon. All right, shifting gears to section 4, understanding pure substances. First off, we have to totally forget the everyday grocery store definition. When you see pure milk or pure ghee on a label, it basically just means it's unadulterated. Nobody sneaked in any cheaper ingredients. But in science, a pure substance has a very strict, absolute definition. It means a substance consists entirely of the exact same type of particles, and every single one of those constituent particles behaves identically. No exceptions.
Next up, Section 5, Elements versus Compounds.
Let's see how this builds our foundation. Elements are the absolute simplest substances in the universe. They cannot be broken down any further into simpler substances by any chemical reaction. Think of these as the literal building blocks of all matter, things like oxygen, hydrogen, iron, or gold. In fact, to give you a sense of how vital they are, more than 45 different elements like silicon, cobalt, lithium, and copper are used just to manufacture the mobile phone in your pocket.
But here is where it gets absolutely mind-blowing. When elements combine chemically in a fixed, specific ratio, they become compounds. Let's look at common table salt, known scientifically as sodium chloride. Now, sodium is a soft metal, and chlorine is a highly toxic, hazardous gas. Yet, when these two elements combine chemically in an exact 1-to-1 ratio, they lose their dangerous individual properties and form a completely harmless, delicious compound that is actually essential for human life. No way, right? Another famous example is water. You take 2 parts hydrogen, which is a fuel, and 1 part oxygen, which supports combustion, and they combine to form a compound that literally extinguishes fire. And you can actually witness a compound breaking down in real time. Unlike a mixture of salt and water, which you can separate just by evaporating the water off, breaking down a compound takes a bit more effort. If you take a teaspoon of sugar in a boiling tube and gently heat it over a flame, you'll see it chemically break down, revealing the raw elements locked inside. It's a pretty stark visual reminder of the structural differences hiding right inside everyday items. And finally, Section 6, the building blocks. Let's bring this all together with the ultimate test. Imagine 2 samples made of iron and sulfur. Sample A is just a mixture. The iron and sulfur are just stirred together. Because it's a mixture, the iron retains its properties. It's still perfectly magnetic, and if you add dilute hydrochloric acid, it produces odorless hydrogen gas that burns with a little pop sound. But sample B is iron sulfide, a compound. Because they are chemically bonded now, the iron is no longer magnetic, and if you add that exact same acid, it reacts completely differently, producing hydrogen sulfide, which is a gas that smells strongly of rotten eggs. Same starting ingredients, entirely different reality. So what does this all mean for us? Well, we've mapped out the entire recipe of reality today, getting into all the details from the macro world of salads and staircases, all the way down to the micro world of elements and chemical bonds. But the most exciting question remains. Knowing how elements combine to form compounds with entirely new, unexpected properties, what incredible new compounds are waiting to be discovered by you? Could the next great chemical combination, maybe a compound perfectly designed to absorb carbon dioxide right out of the air, be the key to solving our greatest environmental challenges? The building blocks are all there, just waiting for the right recipe.